Good morning, everyone. This is Sangeeta from Civil Engineering. Today, I'm going to explain about the equilibrium of a rigid body under three coplanar forces. So, equilibrium of a rigid body under three coplanar forces, which are non-concurrent forces, is that understanding the fundamental principles of static equilibrium when multiple forces act on a rigid body in the same plane, exploring the mathematical and physical conditions that must be satisfied to maintain balance and stability. So, understanding the problem setup is that rigid body characteristics. A rigid body is an idealized solid object that maintains its exact shape and size regardless of external forces applied to it. Unlike deformable bodies, rigid bodies do not bend, compress, or stretch under load. So, this assumption simplifies the analysis by eliminating the need to consider internal stresses and strains, allowing us to focus purely on the external force system and its effects on the body's motion or equilibrium state. In real world applications, thus approximation is valid when deformations are negligible compared to the overall dimensions of the structure, such as in steel beams, concrete columns, or machine components under normal operating loads. So coming to coplanar non-concurrent forces, so the three forces acting on our rigid body share a critical characteristics. They all lie within the same geometric plane. However, unlike concurrent force systems where all lines of action intersect at a single point, these forces have lines of action that do not meet at one location. So this non-concurrent nature is crucial because it means that forces create not only transitional effects but also rotational effects like movements about various points on the body. So the primary goal is to determine the precise mathematical and physical conditions necessary for the rigid body to remain in complete equilibrium, experiencing neither linear motion nor rotational motion when subjected to these three coplanar non-concurrent forces. So what is equilibrium for a rigid body? So coming to equilibrium for a rigid body, static equilibrium, which means a rigid body is in static equilibrium when it remains completely at rest relative to an internal initial reference frame. So, or when it moves with constant velocity, both linear and angular velocities remain unchanged. So, in practical engineering terms, this means the body exhibits no acceleration of any kind, no speeding up, slowing down, or change in direction of motion. So, coming to force balance replacement, the vector sum of all forces acting on the body must be equal to zero. So, mathematically, this is expressed as sigma of force is equal to zero. Summation of all forces is equal to zero. So, this condition ensures there is no net force causing linear acceleration in any direction. So, when forces balance, the body center of mass maintains a state of rest or uniform motion, satisfying Newton's first law of motion. And the third one is moment balance requirement. So the algebraic sum of all moments like talks about any arbitrary point in space must be equal to zero. So this is written as summation of n is equals to zero. Summation of all moments is equals to zero. So this condition prevents angular acceleration and ensures that a body does not begin to rotate or change its rotational speed. So the beauty of this requirement is that if it's satisfied for one point, it's automatically satisfied for all points. So coming to critical insight, both conditions must be satisfied simultaneously for complete equilibrium. So meeting only the force balance condition is insufficient when dealing with non-concurrent forces as unbalanced moments can still cause rotation even when the net force is zero. So coming to free body diagram, which is also called as FBD. For the construction of the free body diagram, it is the cornerstone of force analysis and the statistics and dynamics. So creating an accurate free body diagram is the first critical step in solving any equilibrium problem. So coming to step-by-step FBD construction, isolation. So mentally or physically separate the rigid body from all its surroundings, supports and connections. Draw a clear boundary around the body of interest. And the second point is force representation. Second step is force representation. So you have to show all three forces acting on the body, where each force must be clearly labeled with its magnitude, like force 1, force 2, force 3. So direction indicated by arrows and precise point of application on the body. And third one is the step is coordinate system. So you have to establish a consistent Cartesian coordinate system where XY axis is positioned in the plane containing all forces. So you have to choose an orientation that simplifies your calculations, often aligning one axis with major force or geometric feature. And coming to the next step, it's movement arms. So you have to identify and mark the perpendicular distances from a chosen reference point to each force lines of action. So these movement arms, which are called as lever arms, are essential for calculating rotational effects. So what is the importance of visual clarity? So a well-drawn free body diagram eliminates ambiguity and serves as a visual roadmap for your entire analysis. So it helps identify all forces acting on the system, which prevents overlooking important forces and provides a clear reference for writing equilibrium equations. So professional engineers rely on free body diagrams as standard practice in structural analysis, machine designing, and mechanical systems evaluation. The accuracy of your final solution depends heavily on the completeness and correctness of the initial free body diagram. The common errors such as missing force, incorrect force directions, or misidentified points of application can be caught early through careful FBD construction. So equilibrium equations and 2D coplanar forces. So for any rigid body subjected to the coplanar forces, three independent equilibrium equations govern its static state. So these equations, which represent the fundamental mathematical conditions that must be satisfied simultaneously for the complete equilibrium. So coming to force balance in x direction, summation of f of x is equals to f of f1x plus f2x plus f of 3 is equals to 0. So the sum of all forces components along the horizontal x-axis must be equal to 0. So this ensures no net force cause acceleration in the x direction. So each force component is found by projecting the force vector onto the axis. So where theta is the angle of force which makes it with positive x-axis, which is f cos theta. And coming to force balance in y direction, summation of f of y is equals to f1y plus f2y plus f3y is equals to 0. Similarly, the sum of all forces components along the vertical y-axis must be equal to 0, preventing linear acceleration in the y direction. The force components are calculation as f sine theta. So when forces access various angles, careful attention to sign conventions, which is positive upward and negative downward, is essential for accurate calculations. Next, moment balance about point O. So summation of MO is equals to MO1 plus MO2 plus MO3 is equals to 0. So the algebraic sum of moments or torques about any arbitrary reference point O must be equals to 0. So where Ri is the position vector from point O to the forces point of application, and alpha I is the angle between the position vector and the force vector. Alternatively, where d is the perpendicular distance, moment arm from point O to the line of action of force F. So coming to mathematical independence, so these three equations are mathematically independent for coplanar force systems, providing exactly three scalar equations to solve for three unknowns. So this corresponds to the three degrees of freedom a rigid body has in a plane. The transition in x, translation in y, and rotation about an axis perpendicular to the plane. Applying to three non-concurrent forces. So why moments are critical? So unlike concurrent force systems, where all forces meet at one point and moments automatically sum to zero about the point, the non-concurrent forces create distinct moment contributions about any reference point. Even if the vector sum of the forces equals to zero, unbalanced moments can still cause the body to rotate. This is analogous to applying forces to opposite ends of a wrench. Even if the forces are equal and opposite, when net force is equal to zero, they create a couple that causes rotation. The non-concurrent nature means we cannot ignore rotational effects. With the complete equilibrium conditions for transitional equilibrium, f of 1 f f1x plus f2x plus f3x is equal to 0. Similarly, f1y plus f2y plus f3y is equal to 0. And for rotational equilibrium about point O is MO1 plus MO2 plus MO3 is equal to 0. So where each moment is calculated using the cross product, where MOI is equals to RI bar into cross FI bar, which is equals to RI FI sine of alpha. So here vector is the position vector from the reference point O to the point of application of force, where vector Fi bar and alpha I is the angle between the magnitude can also be expressed as MOI, which is c cot theta. So where di is perpendicular moment arm distance. So coming to geometric interpretation, force triangle, and moment balance. So coming to concurrent forces, non-concurrent forces, and complete equilibrium. So when forces are concurrent lines of action meet at one point, the force vectors form a closed triangle when arranged tip to tail. If this force polygon closes the vector sum of equals 0 and equilibrium exists, no moment calculation is needed because all moments above the concurrency point are 0. Coming to non-concurrent forces. For non-concurrent forces, the force vectors can still form a closed triangle, satisfying sigma F is equals to 0, but this is alone insufficient. So the spatial arrangement of force creates moments that must independently sum to 0. So both force closure and moment balance are required. So for the complete equilibrium, the three forces must be carefully positioned and oriented so that their vector resultant is 0, preventing linear acceleration, and combined rotational effects cancel out, preventing angular acceleration about any point in the plane. When you try to understand physical understanding through geometry, the geometric interpretation provides intuitive insight into equilibrium conditions. Imagine the three forces as arrows with specific magnitudes and directions. For force equilibrium, if you place this arrow tip to tail, they must return to the starting point from a closed polygon. So in this case, a triangle. However, the location where each force acts on the body matters critically. Two force systems with identical force triangles can have completely different equilibrium states if the forces are applied at different points. This is where moment balance becomes essential. It accounts for the spatial distribution of forces and ensures no net rotation occurs. Coming to Varigorens theorem application, Varigorens theorem states that the moment of a resultant force about any point equals to the sum of the moment of its own component forces about the same point. So this principle helps us to understand that when the resultant force is 0, we still need to verify that individual force moments sum is equals to 0 independently. So this geometric perspective bridges the gaps between abstract mathematics and physical reality, making equilibrium analysis more intuitive and accessible. So coming to summary of conditions for equilibrium. For a rigid body subjected to three coplanar non-concurrent forces to remain in complete static equilibrium, two fundamental conditions must be satisfied simultaneously. These conditions are both necessary and sufficient. Condition one is zero net force, where sum of all the forces must be equals to zero. And second one is zero net moments. Sum of algebraic sum of moments about any point must be equals to zero. The first point is you have to draw the free body diagram, and second one is you have to establish the coordinate system, x and y axis. And the third one is you have to apply force equations, and the fourth one is you have to apply moment of equation, and you have to solve simultaneously. So these conditions are necessary and sufficient. If both are met, the body is guaranteed to be in equilibrium. If equilibrium exists, both conditions must necessarily be satisfied. So this mathematical completeness makes the equilibrium equations powerful tools for an analysis and design in engineering mechanics. So if we take an example, beam analysis. So horizontal beam with three non-concurrent forces. So let us consider a rigid horizontal beam of length of 6 meters supported at its ends and subjected to three forces that do not intersect at a common point. So this represents a common structural engineering scenario encountered in building design, bridge analysis, and mechanical systems. So you have to analyze the given force system, and then you have to resolve the forces into components f of x and f of y separately, and you have to add summation of f of y and summation of f of x. And then you have to calculate moments about left hand, which is step 3. And then for achieving equilibrium, to bring the system into equilibrium, we would need to adjust the force magnitudes. We would need to add horizontal force, and we would also need to adjust position or add force. So this example demonstrates how sensitive equilibrium is to force magnitudes, directions, and points of application. So how small changes in any parameter can disrupt the structure. So what are the key takeaways? Your requirements for equilibrium, systematic analysis methodology, foundation for engineering applications, problem solving, versatility. So equilibrium of a rigid body under three coplanar non-congruent forces demands simultaneous satisfaction of both force balance and moment balance. So neither condition alone is sufficient. Both transitional and rotational effects must be neutralized for complete static equilibrium. So this dual requirement distinguishes non-concurrent force systems from simpler concurrent or collinear force systems. So the science of statics begins with understanding equilibrium. Master these fundamental principles and you hold the key to analyzing and designing the physical structures that shape our built environment. So systematic analysis of methodology. Success in equilibrium analysis depends on following a rigorous systematic approach. Construct accurate free body diagrams, Establish clear coordinate systems, resolve forces into orthogonal components, and carefully calculate movements with consistent sign conventions. So the free body diagram serves as a foundation. Errors in this initial step propagate through the entire analysis. So professional engineers rely on this methodological process to ensure accuracy and completeness in structural and mechanical design. So coming to foundation for engineering applications, so understanding these equilibrium conditions is absolutely fundamental in statistics, structural analysis, and mechanical engineering. So these principles form the theoretical basis for designing safe and functional structures, including bridges, buildings, aircraft, vehicles, and industrial machinery. Every beam in a building, every truss member in a bridge, and every component in a machine must satisfy these equilibrium requirements under expected loading conditions. The mastery of these concepts enables engineers to predict structural behavior, optimize designs, and ensure safety factors meet code requirements. So coming to problem solving facility, so the three equilibrium equations, where summation of f of x, summation of f of y, and summation of all the moments of forces provide exactly three independent scalar equations, allowing solution of systems with up to three unknowns. So this mathematical framework extends beyond three force systems to complex multi-force scenarios, distributed loads, and three-dimensional force systems. So strategic selection of reference points for moment calculations can generally simplify problem solving. Choosing points where unknown forces act eliminates their moment contributions, reducing equation complexity. This versatility makes equilibrium analysis an indispensable tool across all engineering disciplines, from civil and mechanical to aerospace and biomedical engineering applications. Thank you.